Okay, say it on this camera just like I did on the backup camera. If you got y prime equal some function of ax plus by plus c, then you can easily change this to a separable equation by letting u equal ax plus by plus c. And that transforms the equation to an equation in u and x and u prime. And the equation then can be rearranged in the form u prime equals a g of x, h of u. In other words, a separable equation. Okay, you can separate out the x and the u. Here, you solve it and then you transform it back to y. And y is just going to be what? U minus ax minus c. Okay, so you need to get y prime and go from there. All right. Now, we've been kind of surveying the kind of problems that you get in section whatever. And let me, again, don't have abundance of time between classes, so I've got to open this. Open a copy of the book in case I've got to look at it. Don't think I will, but I opened the wrong book. You're probably going to open the wrong course. Don't give me pop-ups and view how-to guides. Just open the dang book. Okay. And let me open the class. I've already looked at your homework. Don't see any red flags there. So if you don't have any questions, I'm going to continue kind of surveying the next chapter. And I think maybe I just tried to survey chapter after next, and we don't want to look at that just yet. It was in the reduction of order, so you're into higher dimensional equations. We don't want to mess with that. Now, we talked last time about the logistic equation, and there are situations where the logistic equation applies to something besides populations, but I think you'll find it pretty easy to adapt to that. And we have water escaping a cone. We did that last time. Same principle applies to the other problems that you're going to encounter there. So we get into the next section, which involves mixture problems and so forth, which are always challenging for people. So I do want to, let me open that up and see it. A lot of mixture problems, and you actually get into writing systems of differential equations, but you're not going to solve those for a while. Still, you want to learn to write equations. And then we have LRC circuits, something you're familiar with from physics, but we want to talk about that in a little more detail. Okay, so just a simple mixture problem. And I think we might have talked about a couple of these before, but let's just make sure. We've got a tank, and the tank has so much capacity. So let's just say we got, well, I'm going to use the notation I see in front of me. Let the capacity of the tank be A gallons, and this is tank A. And you have a tank B with B gallons, and you can even have, you have a whole series of tanks, as many tanks as you want. Every tank you add tends to add another differential equation, which is how we get a system of multiple differential equations. So you got 3 tanks. Now let's say you're pumping water into this tank. and this is so many gallons per minute. Now let's just use some numbers. Let's say you're pumping in, I'm going to use GPM for gallons per minute, 10 gallons per minute into this tank. From this tank, I'll use an arrow here to indicate this is pumping into the tank. From this tank, you're also pumping, let's say, 2 gallons per minute. And then from this tank, now we're going to keep this simple. We don't want, we're going to assume all the tanks are full for right now. Now you have problems where not all the tanks are full, but let's just do this with full tanks. So if you want to keep this tank full, you've got 12 gallons per minute coming in here. Well, in that case, you better have 12 gallons per minute being pumped out. Now we're going to keep it simple. We're just going to pump out into this one. We're not going to pump out from this one into both of these because that somewhat complicates the whole situation. Okay. So we're going to do 12 gallons per minute here. Okay. Then we're going to pump from this tank into this one. And let's pump well, let's see. This tank needs to stay full. We're pumping out 2 gallons per minute. We're pumping in 12 gallons per minute. So we'd better be pumping out 10 gallons per minute. Which means, of course, you've got 10 gallons per minute coming into this tank. And if you want to keep it full, you'd better pump out. $10 gallons per minute. Well, now if you've got just plain water in all these tanks, there's no point to all of this because the tanks are just going to remain full of just plain water. However, if you have some chemical, then just think salt. Okay, if you got salt in all these tanks, and maybe you have pure water coming in here, maybe you have salt water. What's going to happen? Okay, well, initially, let's say we have, I'm going to call it solute, whatever it is, the stuff you're dissolving in the water. So initially, let's say you have 10 gallons of solute in A, 20 gallons in B, 5 gallons in C. Could be any numbers. And let's say that A, just to keep it simple, no need that all three of the tanks. Hundred's a nice round number, and if you don't have 100, even if you have different numbers, it's easy to see how they work in, okay? So you have this, A equals B equals C equals 100. We conclude then, and what we want to look at, okay, we want to look at how much solute you have in A and B and C. Okay, so I'm going to QA, QB, and QC, and I'm probably diverging from the text notation. I haven't looked at how they notate these. QA, QB, and QC. Wouldn't be surprised if they use the same notation I do, but they don't always come up to my level, so you don't know. Okay, and I'm still looking at that silly picture. Okay. Now, get back to where I'm looking at the board so I can adjust the camera if necessary. Excuse me. Okay, QA, QB, and QC. And I'll say those are the amounts of solute in tanks A, B, and C, respectively. QA, amount in A, QB, the obvious thing. Now, QA, QB, and QC, when you start pumping, going to be variable. If you got more solute in here than you have in here, then this might tend to increase the amount you have in here, depending on how much you initially have in here and how much you have at a given time. And all that depends kind of what's going in here. The concentration of solute going in. Ultimately, then, the amount of solute you have going, the concentration of solute you have going into the first tank and the initial amounts in the 3 tanks determine what's going to happen in the future for as long as you want. Now, eventually, the system is going to approach constant values. And that, we get into that, we can think of that intuitively and try to predict what the constant values are going to be. But as I've said, we're not going to be able to solve these equations because it's a system of equations. You'll find that we solve systems by setting up matrices and finding eigenvalues and stuff that you're familiar with. And I don't think I'm going to have any trouble being able to solve these systems, but we leave that for later. Right now, we're learning to write differential equations that represent real world systems. Okay. Now, to these conditions, I'm going to add suppose the concentration of a 10 gallon per minute solution coming into A is 0.05. That means 5% of what comes in is solute and the other 95% is water. Before we write the equations, and you'll see why when we write these equations, we want to determine the initial concentrations in each of the tanks. Looking for a word there, okay? How much concentration is there in each tank? So our initial concentrations are what? 10 gallons out of 100 in tank A. So that would be a concentration of 10 over 100. Okay, 10 gallons of solute per 100 gallons of water, per 100 gallons of solution. And in B, we start with 20 gallons of solute, which is 0.20 or 20% solution. In tank C, we have 5 over 100 equals 0.05. Note that if the tanks have different concentrations, not just all 100 gallons, but if we have a variety of concentrations, then we're still going to be able to find this initial concentrations. Okay. The other thing is, concentrations at time t. Another thing that we want to think in terms of are, and I'm listing these in order for A, B, and C, and that should be obvious. Initial concentrate, the concentrations at time t are QA over 100, QB over 100, and let's be specific. QA is the concentration of solute at whatever time, so it's a function of time. So we have QA of T over 100, QB of T over 100, QC of T over 100. Now, big question, first question. And let's move this board over a little bit so sure we can see it. At any time t, we want to write a differential equation that tells us the rate at which the concentration is changing in tank A. Okay. Well, we know the rate at which solute is coming in here. Okay. At 10 gallons per minute, the concentration is 5%. So we have 5% of 10 gallons per minute, which is 0.5 gallons per minute coming in. Okay. So the first thing we want to see is okay, that's what's coming in from the source over here. We also have 2 gallons per minute coming in from tank B. Okay, so 0.5 gallons per minute comes in from the source. So what you have is concentration in B is QB of T over 100 gallons because QB is concentration. Well, right there it is. Okay. So we have that concentration coming in at 2 gallons per minute. So the amount of solute, or the rate at which solute is coming in, and it's a constantly changing rate in this case, is QB over 100 times 2. And that's in gallons per minute. We're going to suppress the units here in a minute. And we have 12 gallons per minute coming out of tank A. So the 12 gallons per minute is carrying solute at concentration QA over 100. So that is being pumped out. Well, now that we have that, it's really easy to write a differential equation. Remembering QA is a function of time, because obviously in this situation, this concentration is continuously changing, and the rate at which it's changing is continuously changing. So we have the rate at which the concentration is changing is, now we're getting 0.5 gallons per minute from the source. Okay, 0.5 plus QB over 100 times 2. And I'm going to write it out that way, even though, of course, we can simplify the numbers. Make sure that looks like a multiplication symbol. QB over 100 times 2, coming in from tank B. Okay, tank B over here. And then it's going to be minus QA over 100 times 12. Now, if you think it through systematically, it doesn't really matter what these rates are. It doesn't really matter what the capacities of the tanks are. None of these numbers matter to the process of writing out the equation. It's going to be the same every time. So it's a very straightforward process to write these equations. And then, of course, we write this as dQA dt, simplifying everything. We have this equation. Now, usually we're going to put the variables in the order A, B, C. So we'd write the negative 12 QA first, and the 0.02 QB second, and then the 0.5 at the end. But maybe the 0.5 goes at the beginning because it's fixed. It's a matter of taste, the way you do it. But when you set up the system of equations, you're going to want to align the A's, the B's, and the C's. Okay. Well, that's one equation. Now we can do this exactly the same thing for tank B and exactly the same thing for tank C. I'm not going to go through all the details. I'm just going to kind of write it out, but I'll say a few words as I do it. And I don't need a full board to do that, so I'll use this one. So we have Same equation I just did. I did that from remembering, but also from reasoning. Okay. The 12 gallons per minute that goes from A to B has concentration QA over 100, and 12 over 100 is the 0.12. It is going out, so we have a negative. 2 gallons per minute coming in from tank B, the concentration is QB over 100. Then we multiply that by the 2 gallons per minute. And if I wrote 0.02, I did wrong, it should be 0.04. Never mind, I don't know what I'm doing. It's 0.02, okay. Got a factor 2 in my head twice. And then you got the half gallon per minute coming in, and that 10 gallons per minute because of the concentration being 5%. If we then just look at the system, we can pretty well reason it out without having to write out every detail. Reasoning is identical to the reasoning we had before. If we look at tank B, we have the 2 gallons per minute going out, the 12 gallons per minute coming in, 10 gallons per minute going out. We'll go ahead and write the numbers that come from A, then from B, then from C. Okay, from tank A, we're getting 12 gallons per minute, concentration being QA over 100. So 12 times QA over 100 is 0.12 times QA, and that's coming in. So we get 0.12 QA. Now everything else is going out. So from QB, 2 gallons per minute is going out at concentration QB over 100. Well, that's going to be minus 0.02 QB. Now we notice that this and this are opposite, this and this are opposite. Okay, because these quantities represent the exchange between A and B. Whatever comes into A is what's going out of B. You just think that through. I wasn't coming up with a really good statement, but it's obvious. Okay, and then in addition to that, we've got this 10 gallons per minute going out of B. Okay, so far we've just got the exchange between A and B. Goes in opposite directions when we're looking at QB. Here we have 10 gallons per minute at concentration QB over 100. So then we're going to have 10 over 100 being 0.1. We're going to have minus 0.10 QB. Now we don't have anything coming in from C, but we could, if we did, we'd have to add some multiple of QC. Now this can be combined to minus 0.12 QB. Okay, so when you write out the final system of equations, you would combine these. For QC, now let's look at it again. You got 10 gallons per minute coming in from B, 10 gallons per minute going out of C. So you're going to have 0.10, well, 10 gallons times Q over QB over 100 is plus 0.10 QB, and 10 gallons per minute at concentration QC over 100 is minus 0.10 QC. So there you have your system. Now I'm going to go ahead and change the form of this system just a little bit so we really see how the system lines up. Because, we've got QAs here, we got QBs here, we got a QB and a QC here, and we can just get rid of that minus 0.10 QB. And combine it with the minus 0.02 QB. To get minus 0.12 QB. And there we have it. It's going to turn out we can represent this system in terms of 3x3 matrix with the obvious entries. And over here, the derivative of the QB column. So might as well anticipate that a little. Would hurt you. You can say then, this can be represented left-hand side by this column vector. In the right-hand side can be represented by this matrix multiplied by column vector QA, QB, QC. Now, I haven't looked closely at the way the text presents this, totally consistent with what I did up to here, except maybe for the notation. Not sure they wrote it as a matrix equation, but knowing that you've had linear algebra and done well, I'm going to kind of do this for you. And the solution of this just involves basically finding the eigenvalues of this matrix. Okay, that's a very straightforward process. We get people in this course who haven't had linear algebra. They can still learn how to do eigenvalues. They don't have quite the insight into it that you will if you've had the linear algebra. And it's a little bit of a stumbling block, but that's not a difficult process. You just get your characteristic polynomial, solve it, put e to the lambda t's into things. It's a little more complicated when you have a system of equations, but not much more. Before we get to this, though, we want to do higher order equations so we can see how an e to the lambda t substitution works there. Before we really want to understand how that's adapted to a matrix equation. But it comes down to this, and it's really not too scary or too difficult at all. Oh, yeah, and I left something off here. I left off the 0.500. So this is like a vector equation, Q prime, the Q vector being the QA, QB, and QC quantities. This matrix, just depending on how the pumping is arranged, times the QA, QB, QC matrix, vector, column vector, it's a column matrix, but okay, plus a non-homogeneous. Looks a whole lot like a linear equation, non-homogeneous linear equation, and you want to make that connection at this point. Okay, so I think it's kind of neat. I think it's kind of great that you can do that. if you're very systematic in it and think about what you're doing, it's not going to be as tricky for you as it is for most students, I think. This tends to be a stumbling block for students. And I've explained it a little differently in a little different order than usual. Hopefully that's going to have some benefit, make it a little easier for you. But it's not excruciatingly difficult. Okay, well, let me pause the video here. My backup video is going to keep going. Okay, we want to talk a little bit about RLC circuits. Resistor with resistance R. Inductor with inductivity L. Capacitor, inductance L. Capacitor with capacitance C. I'm just going to give you the rules for these things, but I'll make a couple of comments to maybe remind you of something you did in physics. I guess it was since last spring or spring before last.
It would have been spring before last.
It was spring before last. Yeah, that was with Dimitri and Alexander, I think. Okay.
Right.
Yeah, I remember what I did to you guys. You know, got a lot of stuff covered, but not sure how well this stuff really sank in. Okay. So you have current. So let's just say you have a current I. Now the current is the rate at which charge transports around the circuit. And everywhere in this particular circuit that isn't in parallel with some other part of the circuit, the current's going to be the same. Okay. Now, and typically in a bigger network, you'll have different currents in the different components, but let's just look at this one real quickly. So okay, I is the rate at which charge passes a different point. If Q is the charge, then that means I is dQ dt. Now, when I say it's the rate, I could say it's the time rate. That's kind of implicit. It's always good. That's why it's derivative with respect to t. It's a time rate change. Okay, so I equals dQ dt. It is then. Okay. Now, you have voltage changes. And you have voltage drop through each component. The resistor, I'm trying to decide if I want to write IR or RI. And I want to write RI because of what I'm going to do. Okay, that's RI. So resistance times the current. Now, I'm not going to go into the physics of why that is, but we're going to take it as the rule, and hopefully remember something about why that is. Which could be then R dq dt. And it's going to get us into second order equation. I wonder if your text actually does second order. If they don't, there's no need for me to do it. Well, I'm going to do it anyway. I'm going to write it out, and then we'll see if we actually get into second order equations. Okay, so you have Ri equals R dq dt. And then across the capacitor, it's going to be Q over C. So you see we got Q, we got a dq dt. And over the inductor, it's L I double prime, I prime, thinking ahead of what's going to happen to Q, equals L times the second derivative of Q with respect to T. Okay, now I'm going to stop the recording just for a second. I hadn't looked that closely. Okay. Now, you got two rules for any network. Okay, the sum of the voltage drops around any loop is 0. That's conservation of energy. Okay, because voltage is energy per unit charge, and you carry a charge around from here to here. You're back at the same point. The electric field's conservative, so you're doing 0 work, so there's 0 voltage change. Hopefully that rings a little bit of a bell, but you don't need it for this course. But you do want to kind of make that connection because it's good for your understanding of lots of things. Okay. Okay. So we got rules. Okay. So these are Kirchoff's laws. Sum of the voltage drops around a loop is 0 because of conservation of energy. Also, the sum of the currents into a branch point is 0. They're called Kirchoff's laws. Okay, and that's because you can't accumulate charge at a point. Because if you accumulate charge, then you got a lot of charge at a point and no charge nearby to cancel it. And very quickly, even with a tiny circuit, you get so much charge that you don't want to get within a kilometer of it. It'll kill you. Okay. It just doesn't happen though, because except on a capacitor, the charge repels itself. So accumulated charge would repel itself so strongly that it couldn't accumulate. So charge just really can't accumulate. Just a few extra charges at a point just can't happen. Okay. And if you want to get into the system of equations and the vector calculus of it, which you understand, and Maxwell's equations and all that stuff, we can prove it, but that's not part of this course. Okay, so you got Kirchhoff's laws, so currents into branch point is 0, and et cetera, et cetera. So we can apply that then to a network of charges. So let's just say we have this where we've got C here, R here, and L here. I'm going to call it C1, R1, and L1. So if I just put ones on these things and say this plus this plus this equals 0, I have an equation. I'm going to do that in a minute. But give you something to anticipate. I'm going to need more board space. Okay. Now let's just do a simple network where I've got a resistor here. Let's say a capacitor here. So now I've got C2 and R2. Well, now charge can't accumulate here or here, or here, or here for that matter. So it means that any current that flows through this has to also flow through this. But since the current branches here, the current that goes through these two is not necessarily the same as the current that goes through this one. So I've got a current. Your book likes to use a lowercase I. I like to use an uppercase I, but I'll go with the book. I've got a current I1, and it's not all the way around this loop. So I'm going to do things a little less carelessly. I'm going to say we have current I1 through R1, and I1 goes through C1. Now we have some other current I2 going through L1, and still another current that has to go through R2 and C2. So I don't have a good place now to label this. So I'm going to put I2 here with an arrow here indicating it goes through this and this. And once you learn to read these and apply the conditions, it's fairly straightforward. Okay. Well, now with that circuit, I can apply Kirchhoff's laws, and I call this I2. It's I3. Hopefully that looks more like a 3. Okay. I'll say the sum of the voltages around the top loop, or voltages around the top loop. And I really mean voltage drops. Okay. Don't have a lot of room, so I didn't write it as voltage drops. That's the proper way to refer to it. Voltage drops around the top loop is 0. So I1R plus I1C1 I1R I would think before I write, would have to erase as much. Plus okay, got a capacitor here. We got some kind of charge on the capacitor. We got I1 passing through the capacitor. What determines the voltage drop of the capacitor is Q1. And what determines the voltage drop on this capacitor is Q2. Okay, so you got I1R plus Q1 over C1. That's your voltage drop here. And then you have di2 dt times L has to equal 0. Now remember that I1 is dq1 dt. So you have, and I'm going to start writing primes, I think. I'm going to write this as R. Okay, I'm going to write this as R dq1 dt plus q1 over c1 plus, okay, remember I2 is dq2 dt. So it's going to be the second derivative of dq2 dt. It looks like a 5 because I got careless with my q. Okay, so we can kind of say, okay, well, we got this. And I can't really say that because Q2 is the charge of this capacitor. And this is the current to a completely different part. Try to get a little less careless here. We'll leave it like this for the moment. Okay. Second loop. Applying the same rules. And incidentally, you might ask, how do I know the direction the current is flowing in? I don't. I'm just going to assume a direction. And when we solve the equation, we'll find what I1 and I2 are and so forth. And if we get a negative, that means it's going the opposite way. So we don't worry about what direction, but we do have to be careful that the direction through here and the direction through here are consistent, flowing the same direction if we're going to use the same symbol. Okay, second loop. We have resistor R2, so we have I3 R2 plus C2 Q2 over C2 minus L di2 dt equals 0. We have to choose a direction around the loop. Just because I've got this current going this way doesn't change the direction around the loop, because remember what we're saying is that from any point in the loop around the circuit back to that point, because of the conservative nature of the field, we do no work, so there's no voltage change. Okay, so if I wanted to go around the loop this way, that would be okay too. So, another thing we need to do that I should have said earlier, for that reason, is we choose this direction around this loop, and I'm going to choose the counterclockwise direction around this loop. Okay, so those little loopy arrows shows the direction that we're using when we think of the voltage drop around the loop, just to make sure we're consistent in doing the voltage drop in one direction around the loop. Okay, so there's a second equation. Well, let's not circle that just yet. So we're going to say that R2 D now I've got a notation problem again. Okay, I want to call this C2 and Q2. I'm calling this R2. That's okay, but I can't really call this Q2. Well, yeah, I can. Okay, except then if I want Q2 to be if I want I3 to be the derivative of the charge here, that's going to cause me problems. So I'm going to change this to Q3 so it matches the I3. And I haven't used it before. Just avoid confusion with notation. I'm going to change this to R3 and C3. This is still di2 dt though. Okay, so and now I'm going to call this Q3. So now I've got this equation. Now I can simplify things a bit because if I look at this point, I've got current I3 coming into this point, current I2 coming into this point, and current I1 coming out of this point. The sum of the currents coming into the point soon wants to reinstall itself, and that would really irritate me. It's done it before, right in the middle of class. And I've told it to delay 2 hours, and it ignores me. But I think we fixed that last time this happened. It was okay. Okay, so I hope I do have my backup camera, and I believe it's still, yeah, still recording, not out of memory there. Okay. Anyhow, we get this. Now, at junction A, let's call this point A. What we have is I1's coming in, I3 is coming in, I1 is going out. So we have I1 plus I2 minus I1. I2 plus I3 minus I1 equals 0. So I2, which is the current through this inductor, is I1 minus I3. So now I can take my di2 dt here and here and replace it by di1 dt minus di3 dt, so that I just have two currents to consider. Okay, so I can rewrite these equations now in terms of just I1 and I3. And that has the advantage that I1 is dq1 dt, I3 is dq3 dt. It's going to make our equations a little bit nicer. Now I can go on with this, but it's going to get a little bit messy, and this isn't assigned for a while. It'll be after we meet our next class, and I'm going to tell you that in case you hadn't noticed, we have faculty and service day on Tuesday and on Wednesday next week. So I'm not going to be able to meet class, which is one reason I'm kind of staying ahead of the assignments here. So I'm not going to see you until a week from today. And I'll tell you now, and I'm going to just I'm not going to put any more on this. I'm getting a little nervous about Zoom. So I'm going to stop recording.